So last time we talked about the hexagonal and we attempted to figure out the planes for the hexagonal and also the direction. So I assigned homework. This is homework number 5, so please check that. It is related to Miller indices for the planes and directions, so try to do that. It is due this Wednesday. So I will try here, guys, to have some examples about Miller indices for the hexagonal, for directions, and for planes, before we start X-ray diffraction. So let's get started. I would like, for example, go with this direction. Let's see how can we do that. So this is A. I believe you can see the direction, guys. So as I can see here, I can have 3 Miller indices for this direction, but before we do that, we need to figure out these 2 points, which is the tail point and the head point. As you can see, guys, the head point right here is 1 along A2, 0 along A1, and we have 0 along A3, and they have 1 along C. But there is another way to figure out 4 Miller indices for this direction, which is just to work with A1 and A2, and then use the equations that I showed you last time to figure out the 4 Miller indices. I will write these 4 equations. If I still remember that, please correct me. So we have h is equal to 1/3. We have 2h prime minus k prime, and I have here k is equal to 1/3. I have 2k prime minus h prime, and also I have I is equal to minus 1/3, I believe, h prime plus k prime. And the last thing is L. It is equal to L prime. Here I will try to figure out h prime and k prime and L prime as Miller indices for this. Yes?
I think it's -1/2.
This one, right?
Yep.
Oh no, it's 1/3. Yeah.
Okay.
It's 1/3, yeah. It is 1/3. That's fine. So normally for the direction we use those square parentheses for Miller indices for the direction, and then we will try to go here to end up with 4 Miller indices, h, k, and then I, and then L. But we need to start from here. So let's figure out those 2 points. The first point right here, and I will use A1, A2, and C. So what I will have 0, I will have 1, so you can see that, guys. So we have 1 from A2, and I have 1 from C. So I have another 1 here. Let's figure out the tail point. So the tail point is 1 from A2 and 0 from A1. See that? Actually, we have this point between A3 and A2. I can extend this like this. So I have -1 from A1, so that works, I believe that. So we have -1 from A1, so we don't need to involve A3 now. And I have 1 from A2, so -1 and 1. So we have 1 here, and also we have 1 along C, so we have another 1. Now to figure out the Miller indices for this direction, we need to do 0, 1, 1, minus, -1, and 1, and 1. This is what we need to do, guys. So 0 minus -1, so that will give me 1. So 1 minus 1, that will give me 0. And 1 minus 1, so that will give me 0. So now we have H prime, K prime, L prime. So we can do something like this now. These are Miller indices, but in 3 dimensions. Now we need to convert those Miller indices to 4 dimensions Miller indices. So what do we need to do? So simply, since this is H prime, and this is K prime, and this is L prime, so we need to substitute that here. And we will do that right now. So I have H prime as 1, so I have 1 here, I have 0 here, here we have 0, and here we have 1, and here we have 1, and here we have 0, and this is simply, so L prime is equal to 0. Let's calculate these guys and see what will happen. So now you can see Miller indices are, so I have 2/3, so we have 2/3, so that's very nice, and I have -1/3, since this is 0, so we have -1/3, that's very nice, and from here we have another -1/3, so we have -1/3, and when we come to L, so we have 0. It is okay to have 0/3 because that's equal to 0. And you can see now Miller indices are 2, -1, and -1, and 0. Yeah, for this direction. And you can do the same thing, guys, with the other directions. Yeah, the directions that I give you in homework number 5. So I believe you can do that. Okay? So this is how can we figure out Miller indices for direction. Now, I will try to figure out Miller indices for planes. And I will pick like random plane here. And I will have maybe, let's do, let's see. So maybe we do this one. And see what will happen. So if we look at to this plane right here, we need to consider the 3 dimensions now. If I look at to this plane, we need to apply the same idea that we did before. I will not use these because these will confuse you. I will just look at to these 4 axes and try to see the points that this plane intersect with these axes. This is what I'm going to do. So here I can see that along A2 we have 1. Along A1, I have -1. Along A3, I have infinity. along C, I have another infinity. So we have, let's do that. So A1, A2, A3, and C. And you can use the same notations that I used in my notes. So you can use x1, x2, x3, x4. So that's fine. Let's see. Now what do we have? So A1 is -1, and A2, you can see that. So this surface intersect with A2 at 1. So we need to have 1 here. And A3, infinity, and C is infinity. So now we need just to get the reciprocal, the same thing that we did with three-dimensional Miller indices in cubic system. So we have -1, and here, so 1/1, it will give me 1, and 1/infinity will give me 0, and this will give me another 0. So now we can do this kind of parentheses. So these are Miller indices for this surface right here. And you can do the same idea, guys, with this surface. For example, I can see that I have 1 along A2. I have infinity along A1, and I have -1 from A3. So I can see that this surface, I can give this surface like different color. Maybe I can do this. That will destroy the figure, but I think we can distinguish this surface from the other one. So we have here 1 from A2, -1 from A3, and we have infinity from A1, and we have infinity from C. So I will do that. So A1, A2, A3, and C. So let's see, what do we have? We have infinity here, we have 1 here, and we have -1 here, and C we have another infinity. So simply Miller indices would be 0, 1, -1, and another 0. Okay? And follow the same idea, guys, when you do homework number 5. So what do you feel? Do you have any questions about this? That looks good? Yes. Thank you so much. So I will now, guys, move to the next chapter, which is chapter 6. I will try to assign you homework from chapter 6. It will not be long, but that homework can help you to understand what is X-ray. If we have enough time, we will study Lawi camera, and we can go through the structure equation, if we have enough time. So let's do that. I will just here to try to draw like crystal structure in 2 dimensions, as you can see here. So what do I mean by these lines? So these lines actually are our planes. So we have some atoms distributed in order along these planes. So we have something like this. We have another row of atoms here. Okay, and of course we have the same distance here, d, between those planes. So there is no difference. Yeah, you can see that I made a mistake here. So this looks like a little bit wider than this one, but actually in reality we have the same distance, so there is no big difference. So what should we do to study this kind of system? It's a system that we can't see, but sometimes we can feel that the material is crystalline, or amorphous by the texture itself. So that can help. But this is not enough, guys. We need to use something that can help us to identify and like know all of the variables that we have here. For example, the space between the atoms, which is the lattice constant. We need to know the space between the planes, for example. So all of that is very important. So how can we do that? We can do that, guys, by using X-ray. So what is X-ray? Yeah, I know that you know that, but it's a good idea to define what's X-ray. So X-ray is electromagnetic wave. And this electromagnetic wave, guys, has a wavelength that matches the dimensions of the unit cell. And that's why we can, we can detect and read some variables here, like d, the distance, the lattice constant, and all of that. So the most important thing is lambda, is the wavelength. So the wavelength here, guys, matches the dimensions of the unit cell. If this is a unit cell in 2 dimensions, you can see that here we have, since I picked D, so I will use D here, and D here, and D here, and D here. But we know, we normally use A for the lattice constant. But let's use D. You know that D represents the dimensions of the unit cell in 2 dimensions. Okay? There is a scientist, a famous scientist, and his name is Bragg. Bragg did very nice experiment. So he attempted to have the idea of the X-ray. So producing X-ray is a different invention that people did. But he used X-ray with crystalline material, and he could manage to study the crystalline material. If I come here and just give you guys simple explanation for how X-ray can be produced, just to show you that before we continue here. So simply, guys, what you need to have here, you need to have a vacuum. So this is kind of vacuum. It is made of, glass. You need to have, guys, here cathode and anode, and you can see, guys, that we have here kind of coil. It can be tungsten coil just to produce electrons. So maybe here we can have kind of voltage. So that can heat up this coil, the tungsten coil, so that can produce some electrons. The electrons can be produced, but they don't have enough energy to jump over this gap. So the best idea, guys, is to try to apply like high voltage here. So you can do that. So when you apply high voltage, guys, you provide these electrons with high energy. So the electrons can jump, and the easiest way for the electron is to hit this metal that we have right here. Okay? There are specific metals that can be used in X-ray device. I believe one of them is copper, so copper can be used. So when the electrons, guys, hit this surface, and we know, guys, another famous experiment, which is photoelectric effect. So the photoelectric effect is something exactly opposite to what we have here. So in photoelectric effect, we produce radiation, and the radiation can produce electrons. Here in this experiment, we produce electrons, and the electrons can produce radiation. So this is what happens, guys. And this electromagnetic wave that can be produced, guys, can be received by a detector, and then we can read it. So yeah, and people during that time, they don't know the name of this electromagnetic wave, so just they call it X, something that they don't know, so they call it X-ray, and it has a short wavelength that can help guys to study what we have right here, which is the crystal structure. But how can we use X-ray to detect and study the crystal structure for the lattice? So how can we do that? So before I explain that to you guys, it's a good idea to try to explain to you what do we mean by if we have like two waves in phase and two waves out of phase. What does that mean? So normally when we draw the wave, so we draw the wave like this. Maybe I will consider here x, so the wave actually is propagating with respect to x and t, but it will have just x here. Okay, and here we have maybe the amplitude. We can use here y as a function of x, for example. So we have something like this. And if I have another wave, guys, and I will try to show you that, so hopefully I can show you that. And if we have another wave, guys, propagating along the negative side of x-axis, moving like this, for example, here we have y of x, maybe this is y2 of x, and this is y1 of x. So now those two waves can go like this. If they are in phase, so what will happen? You will see, guys, that the amplitude will be doubled. So if we have A here, and if we have A here, so the resultant would be 2A, and you can see that you will have a result from this interference, for example. But if we have two waves that are not in phase, like what we can see here, so this, we can see that the crust here is up, and here we have the bottom. So when we like interact with each other, so this will destroy this, and this will destroy this, and you will have zero answer. There is nothing. So that means those two waves are out of phase. Okay? And I can show you that. Maybe I will try to do that here. So let's do this. So that's very nice. I think we have, oh, perfect. Excuse me, so we'll try. Oh, is it with electricity?
Yes.
Yeah. So let's try that. So we don't. Oh, perfect. So let's try that and don't lose what we draw here. Perfect. So let's try to see that. And I will now start. Go to global. can go to a very nice website. It is called O Physics. It is for free. And look for waves. Let's see. Interference and superposition. Maybe this one. Yes. Perfect. So here, guys, you can see that we have two waves. As you can see here, they are in phase, both of them in phase. The first one has different amplitude than this one, so that one has lower amplitude and this one has higher amplitude. So what I'm going to do here, I'm going to adjust the amplitude here, so I can do that. Yes, so they have the same amplitude now. And it will run and see what will happen. So you can see that the resultant wave actually has higher amplitude, actually doubled. Okay, but if I try to have something different, what I'm going to do here, maybe I'm going to change this one and have them out of phase. Let's see what will happen if they are out of phase. I will run them. So at certain time you will have 0. So you will have 0 at certain time. Okay, so this is what will happen if we have out of phase waves. But if they are in phase, so you will see that the amplitude will be doubled. It is exactly similar to the Young experiment, the double slit Young experiment. So you can see, guys, so from the first slit you will have diffraction, and from the second slit you will have diffraction. And diffraction from here, and there is interference will happen. If the interference is, if those two waves are in phase, so you will see like bright spots or bright lines. If the interference between those two waves and those two waves are out of phase, so that will give you dark spots or dark lines. So something similar to that. So I prefer to show you this before we continue, so you understand what do we mean by in phase and out of phase. So that's very good, so we don't need this anymore. And I will turn the light on. So that's very nice. Now I will come here and show you what Bragg did, guys. Actually, Bragg used X-ray source. So this is X-ray source that can produce X-ray waves. And those X-ray waves, guys, can be directed to this crystalline material. So you will see that the X-rays, guys, can go like this. If the X-ray hit the atom, so there's something will happen. It will be reflected to the other side. So this is what Bragg noticed. But this X-ray wave and this X-ray wave should be in phase. Otherwise, you will not have any result. And maybe there is another X-ray go like this, hit this atom right here, and then be reflected, as you can see on the other side. Okay, so that's very nice. And you need to keep in mind that the incident angle here is always equal to the reflection angle. And also here, the incident angle is equal to the reflection angle. So this is very nice. And also we need to keep in mind that the incident and the reflected should be in phase. If they are out of phase, this is very bad thing. So we cannot have Bragg condition. So according to Bragg, guys, so this distance that we have right here is D. can see that this can represent d sine theta, and this can represent d sine theta. If they are in phase, guys, so you'll notice that there is no phase difference between them, and according to Bragg, you will have you will have 2d sine theta is equal to n lambda. So that can happen if the reflected wave and the incident wave are in phase, and of course we know that the reflection law is applied here, so we can see that the incident angle is equal to the reflection angle. So that's very nice. Now let's write this nice equation right here, because we will use it. So n lambda is equal to d sine theta. Let's try and understand what we have in this equation. This angle theta that we have right here actually is the incident angle. Now sometimes people call it Bragg angle. I don't know if I can write the name correctly, but it should be like this. So Bragg's angle. So Bragg's angle. So theta is Bragg's angle. D right here represents the space between the planes. Lambda right here represents the wavelength of the X-ray, or the energy of X-ray. N right here, which is the most important thing that we need to know, guys. N right here represents the set of planes that you have. Okay? If we try to run, run sample and try to get X-ray data, so normally we have something like this, guys. So we have a base that can be rotated 90 degrees. We have a sample that can be placed here. And also we have X-ray source that can target the sample. And also we have detector right here. So this detector can receive the reflected wave. So what people do, guys, if they keep the experiment like this, and they keep just one plane, as you can see right here, so the result of X-ray, guys, that you will have is something like this. If I draw intensity versus theta, I don't know, I'm sorry for that, it should be 2 theta. So this is what X-ray machine measure. If I look at to the result from this run, so you have just something like this, guys. One peak, go up, and then go down. At certain angle. 2 theta. So 2 theta actually needs to be divided by 2 to figure out Bragg's angle. So that can give you the incident angle, which is theta, right here. But if I try to rotate this sample, maybe this is 0 angle, I can rotate the sample to be maybe like this. So we'll see that you will have different outcome. And if you continue to rotate this sample and continue to do that, so you have from 0 to 90 degrees, you can rotate the sample like this. So start with the sample like this, and then you can rotate the sample and then detect theta, the angle theta. So we'll have now different result, guys, because you considered more than one plane. So firstly, you consider this plane, but then you rotated the sample So maybe now we'll consider this plane and continue to rotate the sample. There are many, many planes, guys. So that depends on the position of the sample. Okay? So that will give you a result like this. Another peak, maybe another peak here, small peaks, another peak, something like this. And each one of these peaks, guys, is corresponding to 2 theta. So this is 2 theta 1, corresponding to peak number 1. And this is 2 theta 2. And here we have 2 theta 3. And here we have 2 theta 4. And each one of these peaks that you can see right here represents plane. And this plane can be indicated by Miller indices. So the X-ray device will give you Miller indices. So for example here, you can have maybe 1, 1, 1. Maybe here you have maybe 1, 2, 3. Maybe here you have 1, 0, 1. We don't know. Maybe here you have like 2, minus 1, 1. That depends on the material, the crystalline material that you are using. If you are, for example, studying, if you are, for example, studying if E2 or 3, so there is standard for if E2 or 3. I don't know, this is ferrite or ferric. So this has a fingerprint. It has X-ray data stored in the majority of X-ray machines. If you try to run X-ray for this kind of powder sample, you will have a result. But the good thing, you can compare the result with the standard that you have in the X-ray machine. But if you try to test like new material that you prepared, so that will give you different result. But you can compare each one of these components to the standard that you have in the X-ray machine. So that's very nice. So we know that each one of these peaks, guys, is corresponding to plane, and each one of these planes has Miller indices. So this is very nice. Let's try now to have example, and in this example I will try to show you something. Let's assume that I give you the incident angle theta, and maybe theta is equal to 12.8 degrees. And this angle theta actually is theta 1, which is corresponding to the first peak. And if we are talking about peak number 1, or the first peak, so we can write down here that n is equal to 1. This is the rank of the peak. So we can have n is equal to 1. This is the incident angle for the first peak. And I asked you guys to figure out theta 2. So how can we do that? Simply to do that, so this is the example. So how can we do that? Simply, guys, you need to have that equation and have it here. So we have n lambda is equal to d sine theta. And look at this equation. Are there any variables here? So you can see that it is possible for n to be changed. So if we are talking about maybe peak number 1, so n is equal to 1, peak number 2, n is equal to 2. So this n should be changed. Theta also should be changed, because if n changed, theta should have changed, because peak number 1 is corresponding to theta 1, peak number 2 is corresponding to theta number 2. We have some quantities here that are fixed and never change, which is the wavelength for the X-ray. It will never change. D, also, it will never change. If we, for example, consider the same family of planes, so D will not change. Okay? But if we consider this family of planes, right here, right here, so you can see that this d here is different. So we can have, guys, lambda over d is equal to sine theta over n, and that's equal to constant here. If that's equal to constant, we can do the following. We can do sine theta 1 over n1 is equal to sine theta 2 over n2. We know that for the second peak, n is equal to 2. For the first peak, n is equal to 1. Theta 1 is equal to 12.8 degrees. So now we can do the following. We can calculate theta 2 like this. So we have now theta 2 is equal to sine inverse. What do we have? We have 2 sine theta 1. Or we can write theta 2 is equal to sine inverse, and we have 2 times sine 12.8 degrees. So that will give you guys theta 2, and the same thing can be applied, guys. Okay, but you need to consider here the same family of planes. Maybe the family of planes, like this family, for example, has different direction, but maybe you consider this family, it has different direction, but you will maintain the same D. So, yeah. Okay. So, yeah, this is everything about Bragg's law and how to study the crystalline material using X-ray. Again, there is a very important question. Why we don't use like gamma ray or other electromagnetic waves? What's the reason for that? They don't have the proper wavelength that can help us to study the crystalline material. And that's why, guys, we use X-ray instead. So I believe, yeah, X-ray has a wavelength, I believe from like 0.1 to 10 nanometer. So this is a range. It can be adjusted. That depends on this material, guys. And also there is another important thing. Sometimes, guys, you find this kind of word like K alpha X-ray, K beta X-ray. So that's possible. What's the reason for that? Why do we have something like this? So maybe I would like to share that with you. Or you'll find something like this, so copper K alpha, copper K beta X-ray. So copper means the material that was used here as a target to produce X-ray. But what do we mean by K alpha and K beta? We know, guys, that there are something called electronic shells. We have K, this is how people call them. We have K, and we have L, and we have M, and we have N, and we have O. So we have all of that. If the electron, guys, after you provide the electron with energy, so the electron will jump from lower energy level to higher energy level. But by the end of the day, after some lifetime, the electron will go down and it will release electromagnetic wave. If the electron go down from L to K, so we call that K alpha. And if the electron is going down from M to K, so we call that K beta. It will do the same job, there is no big difference, you will study the material, but there is possibility to produce different X-rays just by considering these electronic shells, like K, L, N. So, and that's why always you see like X-ray, maybe copper, and then you have K alpha. So K alpha means that, and copper means the target that we have right here. Okay, and you can study any type of crystalline material. You can study sodium chloride, you can study diamond, you can study all of that. And it's very important, guys, to do this test. If someone give you like a powder material, and you know that this material is crystalline, and you have the name of this material, but you are not sure if you have the exact material or not, you can do this test. So this test will give you this fingerprint. That can be compared with the standard data. And I used to have like a huge book as a standard data for X-ray. I believe people right now are using a computer to store all of that. But yeah, maybe 10, 15 years ago, people use books to compare. Yeah, you have the X-ray data and then compare with the standard data from those standard books. Yeah, so this is everything for today. So we know what is X-ray, how to use X-ray to study the material. So next session, guys, we will study Lawi camera. It is another way to study the crystalline material. And you will see how Lawi and Bragg, by the end of the day, agree to each other. So if we are using this, Bragg's idea, or using the Lawi camera, so you will have the same result. But right now, people prefer to use Bragg's idea, which is using X-ray and, yeah, using this idea right here. I rotate the sample and then get the data, as you can see right here. Yeah, so this is everything for today, and see you next session, guys. Thank you so much. Yep, you're welcome.